The weldability of materials is influenced by a number of primary factors such as materials, design, process, and service conditions. Material type. Material factors encompass the composition, state, and properties of the base metal as well as the welding consumables employed. These components undergo metallurgical reactions during welding, profoundly impacting weld quality. Incorrect material selection can lead to inadequate weld composition, diminished mechanical properties, and various defects like cracks, porosity, or slag inclusions, thus undermining weldability. Design considerations. The structural design of welded joints dictates stress distribution, directly influencing weldability. Designs should minimize stress concentration, enabling free contraction to mitigate welding defects such as cracks, gaps, or sudden geometry changes. Overly thick base metals or excessive weld volumes can induce multidirectional stress, adversely affecting weldability and should be avoided. Improving process variables. Weldability varies significantly based on welding methods and associated measures. For instance, while gas welding may pose challenges with certain materials like aluminum, other methods like oxygen arc welding can yield satisfactory results. New welding techniques and process enhancements are key to enhancing weldability. Factors such as energy density, temperature, heat input, and shielding methods profoundly affect weld quality and can be tailored to improve weldability, particularly for sensitive materials like titanium alloys. Process measures, such as preheating, controlled cooling, and post-weld heat treatment, play pivotal roles in defect prevention and joint performance enhancement. These measures mitigate heat-affected zone issues, reduce welding stress, and prevent hydrogen-induced cracks. Strategic welding sequence planning minimizes stress and deformation, while post-weld heat treatment alleviates residual stress and prevents delayed cracking. Consider the service conditions. The operating environment of welded structures, including temperature, load conditions, and exposure to corrosive mediums, significantly impacts weldability. Elevated temperatures may induce creep, while low temperatures or impact loads may lead to brittle failure. Corrosive environments necessitate corrosion-resistant joints. Unfavorable service conditions diminish weldability assurance. Weldability is intricately tied to material properties, design considerations, process parameters, and service environments. Evaluating and addressing weldability issues necessitates meticulous selection of materials, welding methods, and process measures tailored to the specific operating conditions of the welded structure. Thank you very much for watching the video. You may consider to subscribe, like or sharing the video, if it is worth doing. Bukhara Tashkent Bishkek Almaty, BTBA, gas pipeline is an operating gas pipeline running from Uzbekistan to Kazakhstan, passing through Kyrgyzstan. The pipeline runs from Bukhara, Uzbekistan through Tashkent, Shymkent, Taraz and Bishkek to Almaty, Kazakhstan. The Bukhara-Tashkent-Bishkek Almaty pipeline is the main source of gas supply for Kyrgyzstan and southern part of Kazakhstan. The diameter of the pipeline is 1020 mm, 40 in, and the annual capacity of the pipeline is almost 22 billion cubic meter (BCM) of natural gas. Construction of the pipeline started in 1967. In 1968, the pipeline reached to Tashkent, in 1970 to Bishkek, then Frunze, and in 1971 to Almaty. The pipeline connects to the Central Asia-China gas pipeline near Akurtob, Kazakhstan, where the Akurtob boosting compressor station was built in 2016. Explore our YouTube channel, Petrosult, for captivating videos covering science, engineering, technology, and energy topics. The primary aim of launching this YouTube channel is to facilitate the exchange and dissemination of knowledge and experiences among professionals and amateurs.